2020 also. His research career span up to 150 research articles in different well-reputed international journals, and his area of interest in research has been the sector and expertise of areas of fluid dynamics like nanofluids, monohybrid and trihybrid nanofluids, heat and mass transfer analysis, Newtonian and non-Newtonian fluids flows. He is a potential reviewer for more than 40 research journals of the world. This is a brief introduction regarding the Dr. Bagh Ali sir, the resource person of the day. With this, I would like to hand over the session to Dr. Bagh Ali, the resource person. So we are looking forward for your message, sir.
Sir, Bagh Ali sir, please take over.
Thank you. Thank you so much, Professor Ashok, for brief introduction about me.
Thank you so much, sir. I'm honored, sir.
Thank you. Can I start my session?
Yes, sir, you can, sir.
Okay. First of all, thank you so much for all of you for giving me a chance to present something about research in your institute. Today, the presentation title is Mitigations Heat Transfer Deterioration in Upward Flow of Supercritical Water. Here is the content of my today presentation. Some basic preliminaries, background of study, motivation, research objectives, methodology, and research problem. Thank you so much, Ashok, because Ashok already gave a brief introduction about me.
Thank you, sir.
First of all, I want to introduce about nanofluids. What are nanofluids? Actually, in short, the researcher use traditional fluids to increase thermal conductivity of base fluids, and different techniques are used to coolant some devices. So in recent 1995, Choi first gave nanofluid idea. The nanofluids basically are colloids which we include solid nano-size particle in base fluids. So we can call it the combination of base fluids and solid nano-size particles are called nanofluids. Actually, nanofluids becomes metal or metal oxides, and these are so much tiny, so we cannot see it in naked eye. So when we include tiny side particle in a base fluids, the thermal conductivity of base fluid is increased. So nanoparticles are very helpful to increase thermal conductivity of base fluids. And if we increase thermal conductivity of base fluids, then base fluid is more efficient as compared to without nanoparticles. And these nanofluids are very useful in industry because they use as a coolant. Advanced flow and heat transfer challenges. Actually, today toughest challenge facing by a lot of industries like microelectronics, automobiles, manufacturing process are thermal loss. Cooling become one of top technical challenge facing high-tech industries such as microelectronics, automobiles, transportation, and manufacturing. I write some here. Applications of nanoparticles or nanofluids. Actually, we can use nanofluids in engineering, engine cooling, nuclear cooling systems, cooling of electronic circuit, refrigerators, enhancement of heat transfer exchange, biomedical applications, cooling of microchips, petroleum industry, surface coating, fuel additives, and lubricants. Heat transfer to fluid at supercritical pressure. Actually, in 1946, Smith investigate heat transfer characteristic of supercritical fluids and observed that the heat transfer coefficient of fluid in this regime showed greater superiority than that at conventional supercritical subcritical pressures. And after Smith, many other researchers studied these ideas and they found that this idea is very helpful in different types of industry. So extensive research activities were carried out to explore heat transfer characteristic of supercritical fluids for the purpose of developing supercritical pressure fusel-fired power plant with improved thermal efficiency. Actually, if we increase base paper's thermal conductivity, and the improved thermal conductivity is very fruitful in thermal power plants. Because if we increase thermal conductivity of any base fluids, then it is very useful for coolant. In recent years, however, there have been renewed interest in this field mainly because of new applications of supercritical fluids, especially in nuclear industry. Actually, many countries are trying to produce electricity with the help of nuclear reactions. In nuclear reaction, there is a heat produced in lot of, and so we need to reduce the temperature inside the nuclear reactors. That's why we use fluids which thermal conductivity is more efficient as compared to traditional fluids. That's why the supercritical fluid is very helpful in nuclear industries. For example, supercritical water reactor, which is one of the most promising generation 4 nuclear reactor system currently under development, is expected to increase the thermal efficiency of currently developed light water reactor from 35% to 45%. It is also expected to be more compact by eliminating coolant, recirculation pump, steam generators, steam separator, etc., which be further reduce the operational and capital cost. And in 1861, first time Maxwell gave the idea of micro size particles. And he concluded that if we include micro size particle in the base fluids, then the temperature of base fluid is increased. But there is a lot of problems because Maxwell used micrometer size particle in a base fluids, and the size of the size of particle is high as compared to nano size particle. That's why the sedimentations occurs, and the real application is difficult in industry because nanoparticle becomes sedimentations at the surface, and so that they can't stable inside the fluids due to unstable in base fluids. They are not useful in practical applications. After Maxwell 1995, Choi gave idea if we reduce the size of particles micrometer to nano size particle, then these particles are stable, more stable as compared to micrometer size particles, and we can use in different purpose. That's why after Choi's idea, the new technology introduced in market. Choi introduced idea of newly developed techniques which include addition of nano-sized particles of good conductors such as copper, aluminum, titanium, irons, and other oxides to the fluids. And Choi gave idea that if we include nano-sized particle in base fluids, and the temperature and the thermal conductivity of base fluids is increased against growing strength of nanoparticle concentration inside the fluids. After Choi idea, Bijrino in 2006 examined the two unusual slip phenomena, effectively Brownian motion and thermophoresis, influence or enhancement of convective rate of thermal energy dissipation. Actually, Choi gave a 7-slip idea in his model, but Bijrino gave idea if we focus only 2 slips like Brownian motion and thermophoresis, then it is enough if we ignore 5 other slips. And after Bijrino, many others researchers enhanced the idea of Choi and Bijrino. Motivations. Motivated by the wide range of applications and quest for improved thermal performance is on its rise because of sophistication in technological process. The use of nanofluid model has provided ample capacity to meet the rising requirement in this research area. It is also worth noting that the occurrence of heat transfer deteriorations in a sudden rise in wall temperature may raise a safety concern as it could potentially damage the tube wall. The motivation for this investigation comes from current lack of work on the mitigation of occurrence of heat transfer deterioration. Research objective: obtain higher rate of heat transfer. Actually, our primary objective is that we want to increase thermal conductivity of base fluids. That's why we want to include nano-sized particle inside base fluid so that we can observe that the thermal conductivity of base fluid will be increased. If thermal conductivity of base fluid is increased, then it is very useful in industries. If thermal conductivity does not increase, so it is not useful in industry. That's why it is our main objective to enhance heat transfer rate inside the base fluids. Develop model to predict the mechanism of occurrence of heat transfer deterioration in supercritical fluids flowing vertically in microchannel using water as a working fluids. Many other researchers use different base fluids like carbon dioxide as a base fluid, but we can also use water as a base fluids. Develop model to predict mechanism of HT in supercritical water flowing upward wavy mini channels, because many researchers use smooth channels, but we want to use wavy channel because the results are more useful if we use wavy channel as compared to smooth channel, because the temperatures inside the nuclear reactor decrease in wavy channel as compared to smooth channel. Obtain optimal configuration, size, positions, number, density, and arrangement of obstacle which can have the most significant effect on STD mitigations. Methodology: simple 2D sketch or draw when simulating a 2D axisymmetric problem. Actually, we are using ANSYS for simulations. The constructive geometries are then meshed to create control volumes. First, we sketch axisymmetric problems in 2D form, and after 2D form, then we transform this sketch into mesh. When all the information required for simulation has been specified, the simulation is then started so that fluid software perform iterative calculation until a converged solution to the numerical equation representing the flow is reached. After the solution is converged, the results are then examined to check that the solution is satisfactory and to determine the required flow data. When the problem is converged, then we can check that if our results which we want to draw, if these are satisfactory, then we draw all the result in tabular form or a graphical form. If results are not satisfactory, then we check again our problems. The obtained result can be visualized with post-processing software, generally including in solver and the contour and vector plot, as well as animation of the calculated quantity can be created. Research problems. Actually, I show a picture which describe my research problems. This picture show nuclear power plant. Here are some different components of nuclear power plants, but the main challenge which we want to solve, which we want to overcome this challenge is
Sir, voice is not audible, sir.
Madam, it is coming.
hello.
Sir, yes, sir, now you can carry on, sir.
Okay. And the main challenge is to reduce the temperature inside the nuclear reactors, because here are nuclear reactions, and due to nuclear reaction, the temperature inside the nuclear reactor increase. And if we does not overcome this challenge, then there is a lot of chance to leakage of this nuclear reactor and chance to blast. If nuclear reactor leaks or you blast, then it can damage human lives and many other things. So our main task is to reduce the temperature inside the nuclear reactors. So many other techniques are used, like here is a pipe where the water flow inside this pipe and reduce the temperature inside the nuclear reactor. So we use supercritical water to reduce the temperature inside the nuclear reactor. And we also use nanoparticle to improve thermal conductivity of supercritical fluids. If nanoparticles are helpful to increase thermal conductivity of supercritical waters, then the temperature inside the nuclear reactor will be reduced. And if temperature inside the nuclear reactor is reduced, then the supercritical nanofluid is very useful to overcome this challenge, to save the nuclear reactor to blast or leakage. Here is actually in 2011 Fukushima accident in France, which create attention of the many researchers to overcome the challenge of high temperature inside the nuclear reactors. So there are many precautions which are useful to avoid the accident. Supercritical water cooled reactors. Actually, here is a figure. Here we can see that at temperature 658 Kelvin, there is variation in thermophysical properties of fluids. We can see here, like I use different colors for different properties, like isobaric thermal conductivity. This color show density, this color shows specific heat, and this color show dynamic viscosity. And we can see here at temperature 658 Kelvin at 25 megapascal, there is a variation in the thermophysical property of the fluids. Actually, from the technical perspective, as supercritical water reactor of water cooled reactors and supercritical thermal power plants. Owing to high pressure, the water as coolant in the single as a supercritical water reactor can be treated as a single phase flow. Since it does not change phase as the temperature increase, however, near the pseudo-critical point like 6558K at 25 megapascal, the physical properties of the fluid change significantly, as we can see in figure B. The high temperature liquid coolant leaving from the core can be like steam directly to drive the turbine. We can see here in figure A. This one is reactor core, and this one is, we use a water pump which pump the water inside the nuclear reactor, which cool the temperature, which decrease the temperature inside the nuclear reactor. Next, heat transfer deterioration in supercritical water reactor. This one is inside view of nuclear reactor. This one is overall mechanism of nuclear reactor, but just our main task is to reduce the temperature inside the nuclear reactor. And in figure B, this one is our geometry. And we use this one, vertical pipe. We take a vertical pipe whose length is 700 centimeters. And we divide this total pipe in three parts, like inlet, this one is our heated section, and this one is outlet. And total length is 700. We divide in 100 centimeter is our inlet and 100 centimeter is our outlet, and the heated section is 1500. And our main task is to reduce the temperature of this heated wall. And in figure C, the phenomena of two-wall temperature peaks was first found in Schitzman experiment. The fluid, if flowing upward, the purple line represents wall temperature. This purple line shows wall temperature. The blue line represents pseudo-critical temperature. And this one, the blue line shows pseudo-critical temperature, and the black line shows the bulk temperature. In this experiment, subcritical water flow upward in an 8 millimeter inner diameter tube with uniform heat flux applied at wall. The operating pressure is 25.3 megapascal and inlet temperature is 324 degree. The pseudo-critical temperature at 25 megapascal is 386 degree. The heat flux is 384.8 kW per meter square, and the mass flux is 449 kg per meter square second. It is clear from figure that there are two peaks, like one peak is this one and other peak is this one. Two peaks of wall temperature along the axial direction. At the beginning, wall temperature increased gradually until reaching pseudo-critical temperature, where it stays the same for a short range of enthalpy. Mitigation of heat transfer deteriorations. Actually, the first peak and second peak. If this peak increase, then deterioration is increased because sudden change in temperature, sudden change in wall temperature. If wall temperature increase, there is chance to leakage of nuclear reactor or your blast. So our main task is to reduce deteriorations. Like if we can see here, the peak is high as compared to second line. The second line is lower as compared to this line. So if we decrease peak, it called mitigation. And our main objective is to reduce the deterioration inside the nuclear reactor. We use concentration of nanoparticles in different types. Like first we try 0% nanoparticle, like we draw a result without nanoparticles. And then we include 3% concentration of nanoparticle inside our base fluids. Then 6%, 9%, and 1.2% and 1.5%. And we observe different outcomes in temperature profiles. If we see when there is no nanoparticle inside a base fluid, then the temperature is 556.768 at peak. And when we just increase 0% to 3% concentration of nanoparticle, then we see here the temperature is 503.025. It is clear from the figure that nanoparticles are helpful to reduce the deterioration of temperatures. Same like when we increase 3% to 6%, then temperature is 472.794 at first peak. Same like at 7th peak, when the concentration of nanoparticle is 0%, then temperature is 470 point something. And when concentration of nanoparticle is 3%, then temperature is 457 point something. So it is clear from figure B, if we increase concentration of nanoparticles, then temperature at first peak and second peak reduce against growing strength of nanoparticle concentration. So we conclude that nanoparticles are very helpful to overcome the challenge to reduce the temperature inside the nuclear reactor. Next, we write about overall performance of this problem, overall performance of outcomes. Here, this one is first peak, and this color show for second peak, like this one. This one is our first peak. If we see in last figure, this one is our first peak, and this one is our second peak. In first peak, 0.30, 0.3%. Then at first peak, temperature reduced 10%. At second peak, it reduced 3%. So temperature variation is more favorable at first peak, because at first peak temperature is more high as compared to second peak. Same like when we increase nanoparticle percentage inside a base fluid is 0.6, then the temperature reduced 15% at first peak and 5% second peak. Same like we can see for other concentration of nanoparticles, the other concentration of nanoparticle is also useful to reduce the temperature. Same like if we check overall performance, this one, I use here 1.5%. When concentration of nanoparticle is 1.5%, then overall performance is high. So it is clear from figure B that against growing strength of nanoparticle concentration, the overall performance increase against higher value of nanoparticle concentration. So it is clear from figure A and B, nanoparticles are very helpful in mitigation of heat transfer in deterioration. Mitigation heat transfer deterioration using VV channel. I draw here like according to our geometry. This one is our inlet, this one is our outlet, and this one is our heated wall. We use heated wall is wavy. It is not smooth. It is not smooth, and we draw a result at different value of nanoparticle concentrations. And we observe that when concentration of nanoparticle is 0.3%, then the temperature line is higher as compared to other higher concentration of nanoparticles, like this one, this peak, this one peak, and this one peak. And when we increase volume fraction of nanoparticles 0.3 to 0.6, it is clear from figure B that the temperature line is lower as compared to volume fraction of 0.3. And same like when we increase volume fraction of nanoparticle from 0.6 to 1.2%, then temperature line is also lower as compared to 3% and 6%. So it is clear from the outcome that the solid tiny particle of nanoparticles are very helpful to reduce the temperature inside the nuclear reactor. And the main challenge was that the temperature is high inside the nuclear reactor, and the main challenge is to reduce the temperature. So nanoparticles are very helpful to reduce the temperature inside the nuclear reactors. And figure B show the outcomes of wavy channels. If we study a same problem for smooth geometry, then our results are more efficient as compared to smooth geometry. So wavy channel is also helpful to reduce the temperature inside the nuclear reactors. Thank you. Thank you so much for your attentions, for your times. Any question?
Sir,
Hello, any question?
sir.
Hello.
Sir. Ali, sir.
Yes, yes.
Yeah, completed, no, sir. Sir, the session is completed, no, sir.
Yes, yes.
Wait, sir, I will ask. So, participants, if anybody has doubts, you can please ask. Once again, all the participants are requested to ask any doubts to the resource persons. Otherwise, you can chat him. Post in the chat, please. Sir is waiting. Sir, I think none of the participants have doubts, sir.
Okay, okay. Thank you, thank you, thank you.
Sir, Ali, sir. I am audible to you, sir.
Yes,
Okay,
yes.
sir. Anyway, sir, thank you for giving this valuable
Thank
session
you,
to us,
thank you,
sir.
thank you, thank you, thank you, thank you so much. Thank you so much.
Thank you. Thank you, sir.
Thank you.
So once again, all the participants are requested to join tomorrow's sessions exact at 2:50. I will send the details through WhatsApp. Thank you.